Welcome to another session in Theory and Applications of Ground Vehicle Aerodynamics. In this session, we will be looking at trucks, trailers, and buses. Trucks, trailers, and buses. Essentially, we have developed a few theories and looked at the car, probably more than all other forms of the ground vehicle. Understandably, there's a lot more cars on the road than there are trucks. But we have a substantial number of trucks and trailers also, and buses, to warrant the study of this and to look at a way to improve the aerodynamics and hence the fuel efficiency, which is the primary, one of the two primary purposes, reasons for studying this subject. The payload is the driving parameter in the design of trucks and buses. Yes, the so-called performance trucks or performance buses, if there's such thing, it's not a commercial production. The mission specification of trucks is to carry load, and the mission specification of most buses is to carry passenger. So it's payload. That's the driving parameter. If we look at this representation, very simple representation, a boxed car, boxed vehicle, look at those dimensions where this will be the longitudinal direction for the vehicle, truck or car, and this is the width of the vehicle, and this is the height of the vehicle. In general, the width to length, that is the ratio of this to this for a car, is more than the ratio of the height to the length. Essentially, we're saying that cars generally have low heights, and the ratio of the height to the length for the bus or truck is generally greater than the ratio of the width to the length. That is, buses and trucks are built high, whereas cars are relatively built low. And the extreme of the low build of cars will be the sports cars or the race cars. In this study, we'll look at light trucks, minivans, sport utility vehicles, essentially comparing them in the amount of drag that they incur. We'll look at medium trucks. Some of those medium trucks can be grouped, split into two, and have one as the high end of the light truck and the other as the low end of the large trucks. So we say medium truck, but it's a very narrow range, what we refer to as medium truck, because again, some light trucks at the high end have a performance equivalent to that of medium truck, and the large ones have a performance that the high end of the medium trucks can fall into. Well, let's look at light trucks, minivans, and sports utility vehicles. Generally, light trucks, they were initially designed for small payload transportation. Essentially a utility vehicle that just moves little things, maybe a small-scale farmer, skills, trade skills people to move their equipment, the one-man business operations to haul the tools that they use in their trade. That was the concept behind the creation of light trucks. Over time, they've evolved into what we call true cars. A through car is a truck that is reversible to a car, or trucker. Some call it through car, some call it trucker. Well, perhaps trucker would be the proper pronunciation because it's a merging of trucks and cars, and that's what a trucker is. It's a reversible. It's reversibly transformable into a car. There are several car design considerations, hence, that are incorporated into the design of light trucks because they've come to be used often as essentially, functionally at least, as cars also. Light trucks and SUVs, they have a higher ground clearance than cars, of course, but in the comparison between light trucks, SUVs, and minivans, minivans are still closer to cars in their design than are trucks and SUVs. And light trucks and SUVs are generally higher from the ground. They have a higher clearance than the minivans. So in this case, this being the minivan, this H, there's the height of the underbody to the ground, we call it H sub n for the minivan, is generally lower than that for the light truck. And the one for the light truck and for the SUV are usually about the same. So you have H pickup is more or less equal to H SUV, which is what has been indicated here. H pickup is more or less equal to H SUV. We're looking at the critical height, the height up to which we can raise the lower, the underbody of the vehicle to avoid lift or lift tendency from the vehicle. And beyond that height, we're actually having separation of bodies, and we undo the benefit we get in the drag reduction and lift to the vehicle. So that critical height, the critical height for the minivan is the lowest when you compare all three of them. The underbody drag for each of these, we see that the underbody drag for the SUV is about the mid value between them. It's higher than the underbody drag, the drag for the minivan, and they're both lower than the drag for the pickup. So what scenario is the drag for the pickup? It's got a higher underbody drag also, and it's got a higher total drag. And we'll look at designs in the pickup, the tailgates, and some of those things that perhaps cause its drag to be higher. Just the general design. You see, this still takes on some aerodynamic feature. This not so much, but certainly more than this. So by just looking for the same size, for the same length and width of vehicles, it's not unreasonable to gesture, to anticipate that the drag here would be the highest, and that is generally the case in vehicle design. We know that the center of gravity for the higher the object, the vehicle is, the higher the center of gravity. So we know that the center of gravity location, which makes vehicle more susceptible to instability, that is, if it's high, that center of gravity location is usually higher for SUVs, slightly for SUV than for trucks. And that's why for quite some time there were roll-up problems with SUVs, because they're relatively higher from the ground. And we didn't have that problem, not nearly to the same extent with minivans. It has to do with the location of the center of gravity. Well, from we'll take this looking at the different phases of the design. Let's look at the front design. The front design, generally, we want to streamline the vehicle leading edge. If a well-streamlined vehicle leading edge can cause a drag reduction of up to a delta CD of up to 0.01, and to have an appreciation for the significance of that, 0.1 mpg is a saving that that would amount to 0.1 miles per gallon because of the drag reduction of 0.01. So if the vehicle takes 20 gallons, which is about reasonable for SUVs and trucks, if it takes about 20 gallons, then you have a saving of about 2 miles. Okay, you get extra 2 miles because of the streamline design in the vehicle, and that's about 2 miles per gallon, and even more so for the SUV. So the longer the distance that's covered, the higher the savings that's obtained from such drag reduction. Every reduction in gas consumption is a benefit, and so it's very important to be able to have a design that is streamlined to the extent that's feasible. As we can see, there's already benefit there. Amongst other things, there's already benefit that can be found there. Now, just because we want the front, the leading edge, the fascia streamlined, does not mean that we're going to be able to get it because of the practicality of the design. Again, remember, trucks and SUVs, especially trucks and trailers and pickups, they are utility vehicles. They are not traditionally comfort vehicles. So the design mission is what dictates the amount of space available for the aerodynamic featuring of the front. The challenges we have is the high cooling needs for trucks and SUVs. They are heavy, relatively, compared with cars, they're heavy duty. There's heavy duty requirements in their function, and so there's high cooling needs for them, for trucks and for SUVs, much more so than for vans, much more so than we have for family vans. And there's vibration of the hood at high speed due to flexible hood design prescription. This second point was not an issue for quite a while until the specification to reduce the impact on the passenger whenever there's crash became more stringent, and was such that whenever there is impact, instead of the hood shooting into the vehicle, the specification now is that the hood is required to crash, to collapse, falling in a vertical direction, much more so than in a straightforward horizontal direction, thereby saving the passenger's life or preventing the steering from hitting the passenger. And that's good, and that's good for safety. Only problem is, to be able to do this, the hood has become more flexible. It's not as sturdy as it was before, and because of that, the stiffness is not there, and it becomes susceptible to wakes and wind gusts especially at high speed as you go. So just the wind alone, the wakes and the winds actually deform the hood in the modern design, the newer design vehicles, and there's also the vibration of the hood itself at high speed. So you have the effect of air, you have the natural effect in the design itself from the structural vibration, and these generate turbulence and do not help in reducing the drag of the vehicle. So what do? It's an optimization design. We look for the best combination between both. Perhaps one of the things that can be done is as we come up with more and more improved material, we can come up with material that are thin, has a thin skin, but sturdy. And one of the things that has been done to ensure that, or to make that contribution, is having stiffness, just stiffness at different locations in the vehicles. So hopefully with the stiffening, the now thinner skin can still maintain the toughness or the rigidity that it would have had if it was of a thicker design. That used to be the case. Let's look at trucks. One of the contributors to drag in trucks is the tailgate, the truck tailgate. And we have different scenarios. This is just a few of all the possible scenarios. It doesn't cover them all. But, well, let's look at these. In this case, the vehicle is going and the air comes over it. This, you have the tailgate open. Okay, this is the tailgate open. This is the tailgate closed. This is a drag net put in. This is the most common scenario that we see all the time. So let's start with this. Let's look at this. We have this logo. It's not covered. Okay, we're not looking at a case when it's covered. When it's covered, it's fine. But generally, we don't have the covers for the trucks. So what happens is this flow goes in and fills this space, but between here and here, it occupies the space, and over time, T, and if the vehicle continues at in its motion, this becomes built up and filled with air, and it becomes an air container by itself, as if this has been covered. So essentially it is covered by air, but that air essentially maintains itself with a little roughening. So you can actually have a situation that's close to, not exactly, but close to what you would have if there had been a bed cover on this, because that layer that settles in, it's bound between here and here. It maintains itself in there, and the other flow that goes becomes superimposed flow on it. So that flow rolls over this this air wall that happens here, and just sheds off to the ground. So essentially, this being there, again, in a relatively steady state situation of the flow becomes such that these stay in, and they create not a solid medium, but an air medium that essentially becomes like a wall for this space, and the flow sheds over and falls off. That's one scenario. The other scenario is the tailgate is open. When the tailgate is open, you don't have that benefit of maintaining this air wall here. So the flow comes and it sheds off. What happens is it hits this place. It actually goes back and recirculates in here and troubles the flow in here. So this flow is not able to maintain the, shall I say, rigidity or the content present here cannot be maintained here because this tailgate is open. And so the flow falls over and sheds off. Also note that in addition, now you have this extra length from here to here over which there has to be drag. So this incurs more drag than this. Then we have a case when there's the drag net that's put there. This is the drag net. Tests have shown that the drag net actually increases the drag more than here, and certainly more than there. So the drag net has not been an aerodynamically beneficial device at all. It increases drag, and as you can see, there's more contact area, and the more the contact area for the flow, the greater the drag that's incurred. So there's drag at each of those holes in the squares, and that increases the drag. So a drag net is lighter, that's true, and it might result in a reduced weight, but as far as aerodynamics is concerned, it actually increases the aerodynamic drag. So a way to compare the benefit of the drag net is to have a drag net of about the same weight, and you would not then see the benefit of weight that the drag net would have incurred. So overall, again, strictly from an aerodynamic point of view, the drag net causes an increased drag. Now, let's look at medium trucks. Generally, the gross weight of medium trucks range from about 14,000 pounds to 26,000 pounds, which is about 6,300 kilograms to about 12,000 kilograms. Okay. Medium trucks are the largest category of commercial trucks available that are being used. This is partly because most of the businesses that we have one-man, two-man businesses, small businesses, and medium trucks serve the purposes of those various businesses. The front of most medium trucks is mainly a bluff body. It's still the case, so not a whole lot has changed, again, because of the mission specification. The primary function of the medium truck is to carry payload and move things around. So not a whole lot of attention has been put to the design. And when attention is put to the design, whenever there is a conflict between creating cooling environments, cooling architecture for the front, for the fascia, and aerodynamic design, cooling goes first, because that's, it's basic to the functionality of the vehicle. Also, the attempt to create an aerodynamic front will cause a longer nose, and that's more material for the design. Even though this might give us a better aerodynamic feature, it may actually add to the weight of the vehicle. So these have to be taken into account, and a compromise made in the design. Medium trucks have a higher ground clearance than light trucks. They're a little higher, and so they have a lower downforce. And we want downforce. Recall, we do want downforce. So as far as the benefit is concerned for stability, when we look at it in the sense of the amount of downforce present, light trucks are better than medium trucks because they have a greater downforce keeping them down than medium trucks do have, essentially because of the height of the medium trucks from the ground. Enhanced traction rather than drag reduction is the primary goal of medium truck design. So it's not that there's no interest in drag reduction, it's just that a higher traction is the more desirable thing. And so emphasis is placed actually a lot on the tire specification for medium trucks, and they're high-performance tires that have high traction to the ground. Also, it's important to know that we've said that there is a lower downforce in medium trucks. That's true. But again, medium trucks weigh more than the light trucks. So their weight, the sheer weight on the ground in the downward direction may be a compensatory property of them to make up for their relatively lower downforce compared with light trucks. Now, let's look at large trucks and buses. This is a typical bus design, and this is a typical light truck design. The point that we want to make here is that generally the width of the bus, which is more or less a straight line on each side, is about the same as the width of the truck. The width is about the same in both cases, the bus and the truck. But the height of the underbody of a truck, which is H1 here, is about 3 times the height of the underbody of the bus. This is the height of the underbody of the bus, H1B, and this is the height of the underbody of the truck. This is very high from the ground, unlike buses. Those are some of the things that to look at in the difference between both in the design. H1 is specified, the height for the bus is specified as equivalent to a hydraulic diameter or an effective diameter, and it's given as 4 times A, that's the frontal area over pi. That's generally how H1 is specified is for the bus. And once we know that for the bus, we know the relative comparison for what it will be for the truck. Again, D is the effective diameter, and A is the frontal projection area, the frontal area of the vehicle. And this is true for the truck and for the bus. So in the case of the truck, the frontal area we will be looking at is, the question is it, does it have a trailer with it, or doesn't it have trailer with it? The A will be different. It will be larger, of course, with the trailer in it, and it's generally done with the trailer in it, on it, so that it gives us a wider area for that. Okay. Light trucks and buses. We want to look at light trucks and buses. First, let's look at the light trucks. Sorry, I don't know what's going on. Okay, light trucks. There are 2 main types of light trucks: the cabin behind engine truck and the cabin over engine truck. This is an example of the cabin behind engine truck. The engine is right here, and here's the cabin. So that's an example of a cabin behind engine truck. And this is an example of cabin over engine truck. The engine is here, and the cabin is right on top of it. So those are the 2 main types of large truck design. Now, for the cabin behind engine truck, the cabin width is generally smaller than the width of the trailer. As you can see, for this, the cabin width is generally smaller than the width of the trailer in the cabin behind engine. Whereas in the cabin or over engine truck, the cabin is generally higher and of a shorter length than that of the cabin behind engine truck. This is an example of cabin behind engine truck. The engine is right here, and the cabin is here. So this is cabin behind engine truck. This is another form of cabin behind engine truck. The cabin behind engine trucks are perhaps the most common large trucks than there are the cabin over engine trucks, although we have those too. But the cabin behind engine trucks seem to be most common, and cabin over engine trucks are probably more common in utility, in severe service utility vehicles. But that's not a hard and fast rule. It's just a common observation. Again, for the cabin over engine truck, the cabin is generally higher and of a shorter length than the cabin behind engine truck, and the cabin is typically the same width as the trailer. So for the cabin over engine truck here, you see that's the same width as the trailer, whereas in the cabin behind engine, the cabin width is generally smaller in width than the width of the trailer. Practice in tractor-trailer spacing is such that the air gap is 40 to 80% of the vehicle effective diameter. What's the air gap? Well, this is the air gap. That's the air gap in tractor-trailer design. So in a design like this, in the modern designs, the design has been such that even that air gap space is used a lot now, so that there's very little, what used to be the entire air gap space is used now, so that there's some space, the air gap space left for the semi trailer. But that space is reduced. It's not as much as it used to be before. But that's the air gap space, and it is 40 to 80% of the effective diameter, which we looked at earlier, the effective diameter. Now, the wider the air gap, the more the aerodynamic drag incurred. Understandably so. The wider this is, the more is going to be the drag, because the flow going in here only increases drag. And one of the things that has been done over time is to put material here. It's used as a bed, a makeshift bed for the trailer driver, and so that there's very little air gap here, and therefore a reduction in aerodynamic drag. So that's one of the things that is done for improvement in tractor-trailer design. Beyond a critical value, we said the wider the gap, the more the aerodynamic drag incurred, up to a critical value. After some critical value, it doesn't matter how wide the air gap is, because we will be treating the trailer and the tractor as two separate entities. But up to that critical point, the aerodynamic drag increases with the air drag. Okay. Now, improvement. The aerodynamic improvement is typically focused on the front section of trucks. Some of the things that are done are the incorporation of the roof deflectors and of some side extensions in the truck design. This was a typical truck design a few decades ago. It's just typical box, and over time there's an improvement. This is chamfered, and with that you can see what would have been the drag here is now reduced, as you have, due to this shape, this chamfer, the flow going over there. So that's an improved design. You still have the side flow. Now, even more improved is the addition of the plate on top here, so that the flow now takes an aerodynamic profile as it goes over there. And this, in addition to that, the cabin space has been well utilized for occupancy and for the reduction of the air gap. So this has multiple incorporation to give us an improved design over what we started with initially. Now, influence of truck lengths. We'll look at those. This is a single trailer. Now, if the trailer is longer, you have a drag coefficient that's up to about 0.3% increase from what it was here, just due to the increase in length. And now, if you have a design that's like this, with the same capacity as this, let's consider this case and this case, having the same capacity, that's the total capacity, the volume on both, is the same, but because this is tandem, there is actually a greater drag incurred here. So it's more economical and aerodynamically more beneficial to have this one long piece than to have coupled carts for trailer whenever possible, because there's increase in aerodynamic drag from this design of the same capacity as this. Okay, that's apart from some other mechanical designs that have to be incorporated for this to latch onto this. Okay, so this is the preferred design to this whenever possible. Now there are practical cases that require the use of this form of trailer over this when goods are shipped, something to do with logistics or the shipping of the vehicles. You want to deliver some first and then another. But as far as aerodynamics is concerned, this is a better design than this for the same capacity. So we'll look at buses. Buses have a continuous uniform surface, just straightforward, like a straight panel. Okay, it's easier to predict the flow pattern in buses and to modify the flow because it doesn't have the air gap and those other intricacies that you have along the sides, especially the front side, the front end of trucks doesn't have that. So it's easier to modify flow there. Now there's the articulated bus, which is also called the accordion bus. It's a long bus with some accordion-like device in the middle to link the front piece and the length piece. For such buses, the length and the capacity are increased by about 50%, but the drag is only increased by 9%. So it's very economical to use that type of bus for transportation of people. You carry more load, more people, more passengers for a relatively reduced increase in drag. In other words, if two separate buses were to be used with the same capacity, you would have had a drag increase of about 40% more than you have by just using that one piece, the accordion bus. And so in that design, you have a 27% total reduction in specific aerodynamic drag. So that's an optimum design. It's an improvement in design when you look at the overall benefit. One of the things that's also getting a lot of attention is the introduction of side skirts. Here's a side skirt here, this vehicle. Most of the designs for the side skirts is this is the vehicle going this way, going forward. So this is the vehicle going forward this way. Okay. The side skirts, they should, to fit the aerodynamic requirement, they should actually be wider in the front and narrower in the back, because that means that you have the flow increase in speed as it goes to the back, so that it can go out at a high speed compared at the back compared with at the front. And that reduces downforce. Okay, the whole idea is for a greater downforce, you want a wider gapping in the front than in the back. But the exact opposite is what's common in design. The side skirts are either straight on both sides or they are wider as you go to the back. Certainly, it's not an aerodynamic reason that causes that design. It's probably a logistic reason. In many of these designs, the side skirt starts from where you have the trailer jack. And if the aerodynamic dictate were to be followed, then this would actually inhibit access to the trailer jack, and that would create its own problems. So I suppose for practical reason, the design here is such that the width of the trailer of the side skirt, that's from here to the other end, is less, slightly less than it is at the back side. And we talked about downforce, and we said, well, with that design that we just indicated, the downforce is actually less. But keep in mind that this is a tractor trailer. The sheer weight alone is enough to take care, to compensate for the detriments of the downforce, or for the little downforce that would have been lost by this design. So it's got its own inherent compensatory design. Have side skirts been found to be useful? Yes, they have been found to reduce the drag by as much as 0.15. That's the drag coefficient, which is a substantial amount. What happens is the flow that would ordinarily just go from under the tractor trailer, from under the trailer, and create turbulence and shoot out from here, now has a wall to cling onto, and that wall becomes a retaining boundary, and that flow does not come out here to cause additional drag on the outside. Rather, the flow forms on this side skirt, which becomes a wall for it and directs the flow in a smooth pattern as it goes to the back. So that's one of the benefits that's the primary benefit of the side skirt. Actually, it's an aerodynamic benefit. Well, there's either weight, so there's either weight from the incorporation of the side skirt, so it becomes a judgment call depending on the load that's being carried. Should we add the side skirt, or should we just leave it because of the weight? It depends. If the vehicle operates at high speed, which is typically the case with trucks on the highway, the side skirt will be beneficial. So what you want to do is use a stiff material that's it's stiff but not heavy. So with that kind of material, you avoid the disadvantage of extreme weight or substantial weight being added by the incorporation of the side skirt, and you gain the benefit of aerodynamic drag reduction, which the side skirt provides. So these are some of the features. There certainly are a lot more features with trucks, tractors, and trailers, but these are some of the features that we look at, and hopefully these would generate your interest in studying more about trucks, tractors, and trailers, and look at the various features, and perhaps come up with ideas to improve these very essential, valuable, useful transportation devices, so that we can keep coming up with improved design and better vehicle. Thank you.